Welcome to the second talk of our tutorial. My name is Alex Kirillov, and I'm a research scientist in Facebook AI research. In the previous talk, Ross has covered the problem of finding objects on an input image and delineating them with bounded boxes. In this talk, I'll introduce the set of pixel-level recognition tasks that are given an image. The aim is to get a pixel-level masks for objects or scenes. My talk is focused on the 2D image plane and pixels on it, and I'll not leave the plane throughout the talk. If you're interested in video or 3D recognition, they will be covered in a separate talks. Here is a general outline of this presentation. I'll talk about 3 pixel-level recognition tasks that all have the word segmentation in their names. I'll define these tasks, explain performance evaluation protocols, and focus on their differences and some common approaches. First, let's start with semantic segmentation. The goal of semantic segmentation task is to assign a semantic label to each pixel in the input image. The segments of the same category, like the sky or tree segments in this image, arise as a byproduct of this per pixel assignment. The standard evaluation protocol for the task is to use intersectionary union for each category across the whole dataset, and then average it out for all categories. Formally, to calculate intersectionary union for a category C, we need 2 numbers. First is the number of pixels across all images that have category C, both in ground truth mask and a prediction mask. And then the number of pixels across all images that have category C assigned to them either in ground truth or prediction masks. Then if we divide one by another, we get an intersectionary union. More formally, it can be presented using the following formula. In this form, it is clear that intersectionary union is a per pixel performance evaluation that does not take into account each segment separately. The per pixel nature of the task and the evaluation metric dictates the way we formulate a machine learning problem to solve it. There is no difference between a wrong assignment near the boundary of a segment or if we assign a sky category to a pixel that belongs to a person class. The penalty in intersectionary union terms will be the same. Thus, it is natural to model the task as an independent pixel classification problem. A fully convolutional network, or FCN, is a great tool for the pixel classification task and is indeed the foundation for most modern semantic segmentation methods. I'll not talk about any specific method here, but I will highlight 2 things that many successful semantic segmentation methods share. Typical FCNs used for image classification gradually reduces spatial resolution of its features to a very small size, as it's not relevant for the task of image classification. To avoid such loss of resolution, modern semantic segmentation approaches use dilated convolutions and/or employ the encoder-decoder structure. Another technique that seems to be universally useful for semantic segmentation is called spatial permit pooling, that applied several pooling operators with different kernel sizes in parallel to supply each spatial position with a long-range context information. There was a stable progress over years for semantic segmentation. Starting from 57% of intersectionary union in 2014, recent methods achieved 85 intersectionary union on the Cityscapes dataset, which is undoubtedly an impressive performance. On this slide, I put the references for this leaderboard shown before. Here are an example of a semantic segmentation prediction for an image from Cityscape dataset. Each pixel is assigned with a color that corresponds to its predicted category, and the segmentation is overlaid with an input image. You can see that the prediction of modern methods is quite precise. Looking at this image, one can ask, is semantic segmentation solved? If given enough data, we can get such results. Well, using the Batteridge's law, you probably could have guessed that I don't think so. In my opinion, one of the problems is related to pixel-wise evaluation with intersectionary union. I'll use a toy example to illustrate it. Here is an image with a kite and a prediction for it. On the right side, you can see how the intersectionary union is calculated in this case. Now, let's add another kite to the image. Even if it will be completely lost by the prediction, intersection of a union will change insignificantly, since the area of the new kite is much smaller than the area of the large kite. This example shows that intersection of a union is dominated by large blobs and is less sensitive to wrong segments with small area. If we go back to the predictions that I showed before, we can identify a few spots that share the same property as the toy example from the previous slide. Here, we have a network predict a small car segment in the middle of a stroller. Note that the area of this error is just incomparable with the area of all cars that were segmented correctly on all images in the test set. So naturally, such error does not really change intersection of a union. Such spurious small segments predicted in areas that are not even close to the real objects of the same category do not influence intersection of a union in a major way. However, they might be dangerous for real-life applications. This issue arises from pixel classification view on semantic segmentation, and I hope that future research in this field will be more segment-oriented and they'll address this problem. Next, let's move to instance segmentation. Instance segmentation can be seen as a direct extension of bounding box detection. The goal is to find objects, but instead of putting a box around them, here we delineate each object with a pixel level mask. Unlike semantic segmentation that does not distinguish two different objects of the same category, instance segmentation requires them to be segmented separately. Common way to measure performance for instance segmentation is average precision, or AP. Unlike intersection of a union for semantic segmentation, average precision is segment-based metric. It treats all predicted objects irrespective of their size in the same exact way. Here is a brief explanation of average precision calculation for instance segmentation. In the first stage, predicted segments are matched to ground truth segments. A pair of predicted and ground truth segments are a true positive pair if intersection of a union is bigger than a certain threshold. Otherwise, these segments are treated as false positive and false negative. Note that this match is done in a greedy fashion starting from a prediction with the highest confidence score, to ensure that no segment match with the two other segments. Then, for each class and intersection of union threshold, we can build a precision recall curve. Using this plot, we average precision across different recall thresholds, across classes and intersection of union thresholds to get our final average precision. To know more details about average precision, I recommend to check COCO dataset webpage that has a nice detailed explanation of the AP calculation. Before moving to instance segmentation approaches, I would like to highlight the difference between semantic and instance segmentation evaluation once more. Unlike semantic segmentation, intersection of a union, where we use intersection of a union, average precision can be significantly lowered by multiple small spurious predicted segments, even if their area is very small. As with semantic segmentation approaches, I will not talk in detail about any specific instance segmentation method. There are two main families of instance segmentation methods. First is top-down approaches. These methods, also often called proposal-based. They extend bounding box detection techniques by adding an additional segmentation head. First, these methods generate proposal boxes. Then, given each proposal box, the segmentation head extracts features that correspond to the box from the intermediate representations of the network and produce mask prediction for each box independently. The key advantage of these methods is their modularity. If you have a new modality that you want to predict, for example, key points for people, you simply add another head that predicts key points for each box proposal. The second family is bottom-up or proposal-free approaches. These methods use fully convolutional architectures to predict several pixel-level modalities that can be then grouped into instances. For example, these modalities can be semantic labels, depth ordering, object edges, the directions to the center of an instance, or the centers of an instances. Then, combining different methods use different sets of modalities, but the important thing here is that there are heuristics or in other networks that can group pixels using these modalities into instances. These methods can often achieve good runtime performance, and using their per pixel prediction then can yield high-quality masks for large objects. However, they often demonstrate inferior performance for small objects in comparison with top-down approaches that treats all objects in the same way, irrespective of their size. Finally, there is a diverse group of methods that are hard to attribute to either top-down or bottom-up approaches. Methods like TensorMask, YOLOCT, or Solar, and many other methods combine ideas from both proposal-based and proposal-free methods. Similar to semantic segmentation, with deep learning, instant segmentation performance has steadily improved. On the slide I put here, I put AP for winning entry in COCO instant segmentation competition in the last years. Interestingly, in the last 3 years, winning entries are all from the top-down family of methods and are all based on mask-RCNN architecture. Without runtime constraints for datasets like COCO, mask-RCNN-based top-down approaches outperforms other methods. Here are a few examples of standard mask-RCNN output. And another one. You can see that it is able to identify objects correctly and delineate them with somewhat blobby mask. What is the reason behind this mask being blobby? Let's see the architecture of segmentation head of mask-RCNN in more detail. While this is a standard head for mask-RCNN, note that most of the state-of-the-art methods based on mask-RCNN still use very similar design for segmentation. The head extracts 14 by 14 feature map for each proposal box. Then, a set of convolution operators is applied, followed by deconvolution that brings the resolution up to 28 by 28. As a result, mask-RCNN produces prediction in 28 by 28 resolution for any object, even if it occupies 1000 by 1000 pixel box in the input image. The output resolution of such mask head, that can be any fully convolutional network, is a trade-off between computational cost and the amount of details the architecture can capture. 28 by 28 mask prediction in mask-RCNN is a compromise that gives you good runtime and does not hurt final performance too much, as most of the pixel lay in the interior of the object, and therefore intersection of unit is not influenced significantly by the lack of details near boundaries. For small objects, 28 by 28 might be more than enough. However, such coarse prediction makes mask-RCNN unsuitable for applications that require pixel-level precision. In what follows, I will present our new work called PointRend that allows top-down instant segmentation approaches to output high-resolution masks with no extra cost. I'll start by looking at other computer vision tasks. While 28 by 28 prediction is okay for instant segmentation, in other subfields, more efficient approaches are used to produce more detailed results without large memory and computational costs. For example, in 3D, grids of voxels cannot really go beyond 64 in cube at the moment. Instead, other representations like point cloud, meshes, implicit functions, or octrees are used to make high-resolution out. PointRend approach I'm presenting today is closely related to the idea of the implicit function and octrees. Another subfield, the 28 by 28 prediction is definitely not enough, is rendering. In order to efficiently render scene, modern methods sample more points in the high-frequency regions and save computation by sampling much less points in low-frequency areas. As a result, the final output has a high resolution, while computation is allocated only to the regions where it is really needed to achieve the desired resolution. Using the intuition of oversampling and undersampling in rendering, we note that it can be applied to instant segmentation as well. In these examples, the red areas does not need a high resolution prediction. In fact, 7 by 7 prediction is flawlessly accurate for this area. On the other hand, high frequency regions cannot be correctly predicted with low resolution masks. Such regions require high resolution. Using this insight, we develop a new method for instant segmentation that resembles under and oversampling in rendering. The PointRend approach starts with a coarse prediction that can be computed efficiently. Then, it gradually upsamples it using bilinear interpolation. refining the prediction only for a subset of points depicted as black dots on the slide. In just a few steps, we can obtain a high-quality mask by refining only a small subset of points. Here is how the inference procedure works in more details. Let's say we start from a coarse 4x4 prediction. We upsample the prediction using bilinear interpolation. Even if the coarse prediction contained only certain probabilities, after the bilinear interpolation, there will be points with uncertain predictions. We select a set of such points. For each selected point, we refine its prediction independently using a light-weighted multi-layer perceptron. As a result, we can quickly increase the resolution by making prediction only for points that the coarse mask is not sufficient. This is a real example of this process. At each step, we take 28 squared most uncertain point for the refinement. Another example there you can see how mask from the wing of this plane is gradually improves when we increase resolution. Now, let's see how the idea of resolution refinement can be implemented. First, a CNN backbone produces a grid of feature representation for an input image. This representation is used to find proposal bounding boxes, and a small efficient segmentation head extracts features extracts features that correspond to each proposal box and produce a very coarse initial segmentation for each object. Using this coarse prediction, we can sample a set of points where we would like to refine it. For these points, we extract corresponding features from backbone's intermediate representation and the coarse prediction using bilinear interpolation. Finally, for each sampled point, we independently apply a multi-layer perceptron to make the refined prediction. This MLP can be seen as an implicit function approach used in 3D in a 3D to recover shapes. During inference, we follow the described iterative subdivision technique to output high-resolution masks. While we can do the same thing for training, it is much simpler to just sample points once and make prediction for this point only. We have full control over the sampling procedure and can bias it towards regions that are more uncertain in the coarse prediction. In our experiments, we found that it is possible to sample as little as 49 points per object, which makes training of the PointRend model very efficient. On this slide, we compare PointRend with the standard mask head applied on top of masker CNN. Note that the boundaries of the PointRend predictions are much sharper. We use red arrows to highlight challenging regions on these images. The standard head outputs 28 by 28 prediction and is not able to capture the same level of details as PointRend can. In our instance segmentation experiments, PointRend outperforms the standard masker CNN with comparable computational costs. For the model trained on COCO, we evaluated on COCO validation set and on annotations from Elvis that correspond to the same categories as original COCO set. Elvis annotations have much higher quality than standard COCO annotations. Note that with Elvis and cityscapes, which also have a high quality annotation, the gap between the standard for convolution head of masker CNN and PointRend is more prominent. PointRend is not limited to instance segmentation only and can be applied for semantic segmentation as well. Our approach can be applied on top of any modern CNN-based method. Here is an illustration of the inference iteration for a DeepLab-v3 based model. In this slide, we compare the standard DeepLab-v3 coarse output and the output of the model enhanced by PointRend. Note that thin long structures are captured significantly better with PointRend. In our experiments, using Cityscape's semantic segmentation benchmark, we show that both DeepLab-v3 and semantic FPN significantly benefit from the addition of the PointRend model. To wrap this part up, PointRend is an efficient technique to output detailed high-resolution segmentation and can be applied as a plug-and-play on top of any CNN-based image segmentation method. The code is available in the Datacron 2 GitHub repository. So next, I'll move to panoptic segmentation, the task formulation that actually combines the instance and semantic segmentation that I covered before. While instance segmentation is focused only on countable objects that have notion of instances, semantic segmentation often use a wider set of semantic labels that include stuff categories like sky, water, or grass. For semantic segmentation, the goal usually to assign the label to all pixels, but there is no way to split different objects of the same class. For someone outside of our community, it might seem strange that these two tasks are considered separate. But we know that they have a different history. Very different approaches were developed for this task, different data sets, and different metrics are used to evaluate their performance. So let's see how instance segmentation prediction is looking for one particular image. What can we say about this scene? Well, we see the skis, so likely it's about mountain or cross-country ski. The person in the middle can be a kid going down the slope. Now, let's add semantic segmentation prediction to it as well. Now, I think our understanding of general scene context has changed quite significantly. We see that the person is actually in the air. Overlaying the prediction with actual image, we can see that our understanding of the layout was actually correct. On the other side, we can see how semantic segmentation prediction looks like for street view. The overall geometrical layout is quite clear. We know where we can drive and where we cannot, but what is not enough is that is not enough if we're trying to navigate the world. So semantic segmentation has no notion of individual objects, but in the case of navigation, we really want to know whether this blob of people wants to cross the street or not. Adding instance segmentation prediction, we can reason about each individual person separately. Here, if we overlay it again, we can see that this unified segmentation prediction gives us a lot of useful information about the scene layout. These were just two examples, but I hope you're now on board with the need to have both semantic and instance segmentation prediction for real-world scenarios. In what follows, I will use the notion of things and stuff categories. The thing categories have instance level annotations, and stuff categories do not. While instance segmentation usually works with things only, for semantic segmentation it is common to use both things and stuff classes. So the idea behind panoptic segmentation is to unify these both tasks into a single thing. Well, the idea is not new. There were papers considering some kind of unification more than 10 years ago. However, it did not become a mainstream task back then. In my understanding, the main reason for that was the lack of appropriate data and the lack of proper evaluation process for the unified task. Different terms were used to describe the different version of the unified task. For example, image parsing or scene parsing. The most recent one is panoptic segmentation, and this talk is about this specific format. Panoptic here means seeing everything at once and highlight the unified nature of the task. Let's define the panoptic segmentation task formally. The goal is to assign a semantic label to each pixel on the image and simultaneously segment different objects of the same class separately. Panoptic segmentation is a generalization for both semantic and instance segmentation. Given panoptic segmentation prediction, you can obtain both semantic and instance segmentation. Panoptic quality is a new metric developed specifically for panoptic segmentation. So panoptic segmentation refers to the specific task formulation coupled with the evaluation protocol. I briefly summarize the metric using a simple toy example on the slides. Similarly to average precision, panoptic quality is a segment-based metric that treats all segments in the same way, irrespective of their size. For each category, we have a set of predicted segments and grouch of segments. First, we perform matching using the intersection of union. If predicted and grouch of segments have intersection of union larger than 0.5, then the pair is a true positive pair. Otherwise, these are false positive and false negative pairs, false negative and false positive segments, and we assign them to the corresponding sets. Since ground truth and prediction for panoptic segmentation has no overlap between segments, the matching obtained using the rule is actually unique. Next, we calculate panoptic quality by summing up the intersection of a union for all matched pairs and divided by the number of such pairs, plus the penalty for false positive and false negative cases. Panoptic quality is a single unified metric that works exactly the same way for both things and stuff categories. Similarly to average precision, and unlike intersection union for semantic segmentation, panoptic quality penalizes spurious small segments of any category. Next, similarly to semantic and instance segmentation, I will describe general ideas behind approaches for panoptic segmentation. First, I'll describe a non-unified methods. These methods do not treat all classes in a single unified way. Instead, they produce semantic segmentation for stuff classes and instance segmentation for things classes, using either two separate or a single network. These two modalities are then combined together, either through a heuristic or an additional network that takes into account interconnections between different classes. These approaches usually have separate instance, semantic, and combined losses, and therefore I don't see them as truly unified methods, even if it's a single network. Other set of approaches stems from the bottom-up approaches for instance segmentation. This approach predicts semantic segmentation as part of the pipeline, and therefore can be naturally extended to predict full panoptic segmentation. These methods demonstrate superior runtime performance. So if you need something small and fast for panoptic segmentation, you'll likely look into bottom-up approaches. Finally, I would like to talk about very recent work that proposed a fully unified approach for panoptic segmentation. Detection transformers, or DETR, is a new method for object detection that combines CNN with transformer to predict bounding boxes directly without non-maximal suppression. Ross has talked about this method in detail in his talk. To adapt this method for panoptic segmentation, instead of predicting bounding boxes for just things, we can make the network to predict bounding boxes for both things and stuff categories. So in this example, in addition to the boxes for person and the surf, we expect the network to predict boxes for the ocean and the beach as well. This way, things and stuff segments are treated in the same exact way. Now, to get masks for each segment, we will use the embeddings we got as the output of the transformer. Each embedding corresponds to a thing or stuff, object, or entity predicted by the network. We extend the architecture with a network that transforms these embeddings to segmentations. First, an attention layer is used to transform the embeddings into low-resolution spatial feature representations. Then, these representations are gradually upsampled by using an FPN or feature pyramid network style architecture that utilizes intermediate representations from the backbone. This architecture outputs a mask prediction for each embedding that then goes for an argmax operator to output the final prediction. The most interesting part of this approach to me is that it does not consider things and stuff separately. Instead, they're all predicted in exactly the same unified way. DETR produces a high-quality panoptic segmentation where all segments are well aligned between each other. It outperforms current state-of-the-art for panoptic segmentation. I hope that this method will inspire more work on a truly unified methods for panoptic segmentation. With that, I would like to conclude and thank you for your time.